Welcome to Basic Mathematical Analysis class. Today we will discuss about intervals. We know that by the order property of R, we can have some ordering to the real numbers. Thus, the order relation on R determines a natural collection of subsets called intervals. Called intervals. There are five types of intervals. Interval. First, it is split into open interval. Next, closed interval. Next, half open, or half closed. Half closed intervals. Fourth one, infinite open interval. Infinite open interval. And the last one, infinite closed interval. Infinite closed interval. Now let us examine what are these. Open interval. Open interval means we are having A, B are real numbers with A less than B, then the open interval determined by A and B. Open interval determined by A and B is, we are representing this as a set AB that's equal to set of all x belongs to R such that A less than x less than. So this is called open intervals. Now it means that this interval contains all the terms in between A and B, right? Next coming closed interval. Closed interval means if again A, B belongs to R and A less than B, then the closed interval determined by A and B, we are denoting it as AB is nothing but the set x belongs to R such that A less than or equal to x less than or equal to B. The difference is we have included the endpoints, right? We have included the endpoints. Now half open or half closed interval. The half open or half closed interval determined by A and B. So it is we are denoting it as either A closed B. So the meaning is set of all x belongs to R such that A less than x less than or equal to B. This is the one way, and another way of this is uh, closed A, B open. So this is set of all x belongs to R such that A less than or equal to x less than B. So this is called the half open intervals. So second and third. Now for infinite open intervals. Infinite open intervals means the sets of the form will denote it as either A infinity, that's equal to set of all x belongs to R such that x is greater than A. And you can have another notation also, and denote that as minus infinity B. So this meaning is that set of all x belongs to R such that x is less than B. So these two are called infinite open intervals. Okay. Next is, here you should note that it is containing no upper bound and this containing no lower bound, and this one bounded, this is bounded, and this is also bounded, but this is not bounded above and this is not bounded below. Now coming back to infinite closed interval. Infinite closed interval means infinite closed interval. Closed interval we can have the set as A infinity, that's equal to set of all x belongs to R such that x is greater than or equal to A, right? And you can have another one minus infinity B. So this implies set of all x belongs to R such that your x value is less than or equal to. So this is the category of intervals. Step into five categories. One is open interval. Open interval means this is of this type. Closed interval, this type. Half open, infinite closed intervals. Now we can note some more things. Writing a set mark. First one, the points A and B are said to be the endpoints of the interval. Okay. Now the second one, the entire set R, the entire set R can be considered as can be considered as an infinite interval, an infinite interval as minus infinity, infinity. Now it should be noted that no points no points is an endpoint of minus infinity infinity. Also, minus infinity and infinity are not real numbers, not real numbers, but only symbols. But only symbols. So we have defined an interval, and there are five types of intervals. Now we will have the remark as the points A and B are said to be the endpoints of the interval. Now we can take the entire real line as an infinite interval of the time minus infinity, infinity. Now then it can be noted that this infinity and minus infinity is not going to be real numbers, they are just symbols. Now we will pass to the characterization of intervals. Characterization of intervals. We know one evident result about the interval. If I is an interval and AB belongs to I with A less than B, then what's the condition? Then if A less than some Z less than B means Z also belongs to I. Or else we can say that if AB is in I, then closed interval, this is contained in I. Am I right? So this we have known the fact. Now the characterization is that if any set is given which is having this property, then that set is nothing but an interval. A very evident property evident property of an interval of an interval I if x comma y belongs to I and x less than t less than 1, then t belongs to I, right? This is the evident property. Now we will use this as the characterization of an interval. That is, if any set is having this property means that set will reduce us to an interval. So 2.5.1 characterization theorem. Characterization theorem. If S is a subset of R, if S is a subset of R that contains at least that contain at least 2 points, and has the property and has the property if xy belongs to S and x less than y, then interval xy is contained in S. Okay, then S is an interval. Then S is an interval. So this is the characterization theorem. So what this theorem says? This theorem says that whenever we are having a subset of R that contain at least 2 points and having the property if xy belongs to S and x less than y, then the interval xy is contained in S. Then S is nothing but an interval that we want to prove. So how to prove it? Let us see. Proof. We will discuss this in S, by categorizing S into 4 cases. So there are 4 cases to consider. 4 cases to consider. Case 1. S is bounded. S is bounded. So this is the first case. S is bounded. In this case, it has a supremum and infimum. Supremum and infimum. So let A equal to supremum of S and B equal to infimum of S. So we have assumed that S is bounded. Since S is bounded, it should have a supremum and an infimum. Now if some x belongs to S, then evidently this x should be A less than or equal to x less than or equal to B, right? Am I right? So what it means? So this implies your x belongs to closed interval AB, right? So we have proved one part. Then your S is contained in closed interval AB. Call this as equation 1. So we have got S is contained in closed interval AB. Now we will show that open interval AB is contained in S. So for that, what we have to do, we have to take an element in here and show that that element belongs to here. So let some Z belongs to open interval AB. So which implies A less than Z less than B, right? which implies Z is not a lower bound of S. Lower bound of S implies that is not a lower bound of S, which implies, what is the meaning of this? There exists some number, some x belongs to S such that your x is less than Z. Now also here Z is not an upper bound, right? Because Z is lying between infimum and supremum. So this is not an upper bound, which implies there exists some y belongs to S such that this y is greater than Z or Z is less than y, right? So call this as double star. Now what we have? This we get this from star and double star, we get x comma y belongs to S and x less than y, right? And for the condition x less than x less than Z less than y. Okay, then we have assumed one property for S. What was that? This is the condition. We are having property for S as, see, xy belongs to S and x less than y, then the closed interval xy is contained in S. So using that property, then the property of S, what are you having? We get closed interval xy is contained in S, which implies since your z value is between x and y, this z belongs to S. What was that? That was an element from AB, right? Now we have got that belongs to S. So hence we can conclude that S is contained in interval AB. I'm sorry, it's on the other way, right? So we should have this interval is contained in S. So the interval is contained in S. Now call this as your equation 2. Okay. Now we are having equation 1 and equation 2. Now if A and B belongs to S, if A and B belongs to S, then from 1 and 2 we get, see, we have proved that here is nothing but equation 1 gives us S is contained in closed interval AB. This was your equation 1, and equation 2 was open interval AB is contained in S. This was equation 2. Now if AB belongs to S, AB also belongs to S means we get S is nothing but closed interval AB. Am I right? So we have proved that S is an interval. Now suppose some member is not there, that is A is not belongs to S, then what will happen? Now if A does not belongs to S and B belongs to S, then your S is nothing but open A, closed B, right? Now if A belongs to S and B does not belongs to S, then what are you having? S is equal to closed A, open B. And next case, if A does not belongs to S and B does not belongs to S, then in this case your S is nothing but open interval AB. Thus in this case S is nothing but an interval. Now case 2. Case 2. In case 2 we will assume that S is bounded above but not below. So we will assume in case 2 as S is bounded above but not below. Now since S is bounded above, we should have supremum, right? So since S is bounded above, it should have a supremum. It should have a supremum. So we will assume that that's supremum. Let B equal to supremum of S. Then X belongs to S. Then this X value should be always less than or equal to B, which implies your X belongs to minus infinity B or close to B, right? So we can have close to B here. Close to B. Which implies your S, X belongs to S means X belongs to this. So S is contained in open minus infinity close to B. Close to B. Now to get the reverse inclusion, okay, to get the reverse inclusion, let Z belongs to minus infinity B. Now we want to prove that this Z belongs to S. Since the Z value is less than B, that's equal to supremum of S, implies Z is not an upper bound, right? Z is not an upper bound of S, which implies there exists some Y belongs to S such that Z is less than Y. Also S is not bounded below, right? Bounded below. Therefore, we can find therefore we can find some x belongs to S such that this x value is less than z. First of all, S is bounded above. So bounded above means it should have a supremum. That supremum we are taking as B. Now if you are taking any element of that set, that element should be less than B, right? Now to get the reverse inclusion, let Z belongs to minus infinity B. Now this meaning is that Z is less than B, right? Now Z is not an upper bound of S. If Z is not an upper bound of S, there should exist an element, at least one element, which is greater than this Z. So that element we are taking as Y. So Z is less than Y. Now also the S is not bounded below. S is not bounded below means if you take any element, we can go for an element which is lesser than the given element. So once you took Z, we can go for an element which is less than Z. You take that element as X. Now what you are having here, X less than Z less than Y. Thus we have X comma Y belongs to S. X comma Y belongs to S such that X less than Z less than Y. Then again by property of property of S, we get closed interval xy is contained in S. So this implies your Z belongs to S. From where you took this Z? Z we have taken from minus infinity B. Now we are getting that Z belongs to S. Now Z is an arbitrary point since Z is an arbitrary element. Z is an arbitrary element in minus infinity B. We have minus infinity B is contained in S, which implies your S is equal to minus infinity B. If this B belongs to S, right? Now, if our supremum does not belongs to S, then our S should be minus infinity B open, right? So in the second case also, we have proved it is an interval. Now we will pass to case 3. Case 3. S is bounded below but not above. S is bounded below but not above. S is bounded below but not above. This case we can similarly deal as we have taken in case 2. Because it is bounded below, then it should have an infimum. So any number when you are taking from S, that should be greater than this infimum value, right? So then if S is bounded below, it should have an infimum. should have an infinity. So let A equal to infimum of S. Then, as in case 2, we can show that S equal to A infinity if A does not belongs to S, and S equal to closed A infinity if A belongs to S, right? Since it is bounded below, it should have an infimum. Okay, so when you are having, so if you're taking an X belongs to S and infimum of S is equal to A, then any X belongs to S implies your A is less than or equal to X, which is less than infinity, right? So this X belongs to the interval. What is the interval? Interval, closed interval A infinity, right? So from this you will get your S is contained in closed interval A infinity. Now to get the reverse inequality, what we have to do? We have to take a element in Z belongs to A comma infinity. Now since Z belongs to A comma infinity, Z value should be uh, A less than or equal to Z. Also, this is not bounded above. Then we can easily find another number B such that that is in between A and B. Now, A and B belongs to S, A and B belongs to S, and A less than B. By using the property of our set S, we will get closed interval AB is contained in F. That means your Z belongs to S, right? So you will get closed interval A infinity is contained in S. Now we can check this into two cases: if A belongs to S and if A does not belong to S. So if A belongs to S, S is nothing but A infinity. If A does not belong to S, this will reduce as A infinity. So this is the third case. Now for the fourth case, right? The case for S is neither bounded above nor below. So S is neither bounded above nor below. So this is the last case. Since S is neither bounded above or below, if you're taking any real number, we can find two other real numbers such that x less than z less than y. Now since S is not bounded above and below, I am writing as not bounded for any real number, z. We can find a comma b or x comma y. We can find x comma y in S such that x less than z less than y. Then by the property of S, then by the property of S, we get the interval xy is contained in S. Therefore, Z belongs to S. Okay. Therefore, this Z belongs to S. Now, already your S is a subset of R, set of real numbers. Now, what you have shown is if Z belongs to R, then you have taken Z as a real number, right? See, uh, for any real number we have taken Z. So Z belongs to R, then what you got? Now Z belongs to S, right? Now we got Z belongs to S. Since your Z is arbitrary, Z is arbitrary real number, arbitrary number, it follows that S equal to R. That's nothing but minus infinity, infinity I can take. Thus, in all the four cases, S is an interval. S is an interval. So in today's class, we have seen what's an interval and 5 kinds of intervals and the characterization of the interval. Okay, so intervals, we can classify the intervals into 5 categories and characterization of interval. What was that? That is, for set S subset of R is contain at least 2 points with the property that if xy belongs to S and x less than y, then the closed interval xy is contained in S. Then S is an interval. And we have proved this by using 4 cases. Case 1, S is bounded. Case 2, S is bounded above but not below. Case 3, S is bounded below but not above. And case 4, S is not at all bounded. Okay, so with this, I'm winding up today's session here. Thank you for your patient listening. Thank you.